Millions of drivers step into the freezing ambient air, slide into their seats, and turn the ignition key. The engine catches with a familiar roar, and within a single second, the gear selector is forcefully pulled into drive to rush out of the driveway. It is a completely mundane daily ritual. Yet what none of those millions of drivers can see is the terrifying, microscopic mechanical violence unfolding deep inside the metal block during the first 3 seconds of that startup sequence. At that exact moment, the lubricating oil is resting completely stagnant in a pan at the bottom of the engine. The heaviest, fastest-moving components of the engine above are spinning virtually dry. The driver might hear a brief, hollow metallic tap that quickly fades into a smooth hum. That noise is the acoustic signature of boundary friction, actively stripping away single layers of atoms. The precision keeping this machine alive relies on maintaining a physical gap between the heavy steel components. That required gap is less than 1/100th the diameter of a single human hair. If the fluid takes 3 seconds to travel from the oil pan to those top bearings, we have to look closely at the mechanical destruction happening in that dry window and why this highly normalized daily habit silently marches the machine toward unrepairable death. When this microscopic boundary friction accumulates in a standard commuter vehicle, it becomes the leading cause of complete engine seizure. Replacing that fused block currently ranges between $3,000 and $14,000, depending on the complexity of the powertrain. Scaling up to extreme industrial applications, the consequences of this microscopic fluid starvation transition from expensive to highly destructive. In commercial rail transport, ignoring a simple oil maintenance warning forces heavy steel locomotive bearings past their thermal limit, permanently welding a massive 4,000 horsepower engine into a single block of molten scrap. We see this exact mechanical mechanism threaten commercial aviation. On November 4, 2010, Qantas Flight 32, an Airbus A380 carrying 469 passengers, experienced a terrifying uncontained engine failure mid-flight over Indonesia. A microscopic manufacturing error in a single internal oil feed pipe caused a high-pressure leak. The resulting localized starvation critically weakened the intermediate turbine drive arm in the Rolls-Royce engine until the disc broke apart from overspeed. Similar undetected fatigue cracks, exacerbated by metallurgical flaws, led to a massive uncontained failure on Delta Airlines Flight 1288, sending high-speed steel shrapnel tearing completely through the aircraft's fuselage. The underlying physics dictating these failures are identical. The destruction of a family sedan parked in the suburbs and a massive commercial jet in the sky both start with the breakdown of an invisible, microscopic gap. This animated diagram shows how an internal combustion engine survives through hydrodynamic lubrication. The rapidly spinning crankshaft continuously drags viscous engine oil underneath it to create a high-pressure liquid wedge that physically lifts the heavy metal components apart. The measurements dictating this separation are astonishing. The gap holding the steel apart, known as the minimum oil film thickness, is only 0.5 to 1.6 microns. Gravity breaks this state every single time a vehicle is parked overnight, pulling the oil down into the sump pan. This creates a dangerous 1 to 3 second lag before the pump can pull the cold fluid back up to the top of the block. During this critical dry window, the engine relies entirely on an organometallic chemical additive in motor oil called ZDDP, which functions as a microscopic shield barely 2 microns thick. ZDDP reacts strictly to intense heat and pressure by decomposing and baking a glassy iron-zinc polyphosphate film directly onto the metal surface. Under low oil pressure conditions, the engine grinds away this replaceable zinc layer instead of the expensive base steel. The survival of the entire rotating assembly during a cold start hinges completely on this temporary glass-like shield, absorbing the friction just long enough for the hydraulic pressure to normalize. If the oil pump fails to deliver fluid past that 3-second window, the extreme friction instantly burns away the chemical shield, exposing the bare SAE 52-1000 bearing steel underneath. Looking at this cross-section of a connecting rod bearing, we see what happens without that incompressible liquid cushion. The massive cyclic downward loads of combustion force the rod to slam onto the spinning crankshaft. The microscopic peaks of the metal surfaces collide violently. Between 3 and 30 seconds of starvation, these collisions generate immense flash temperatures. The localized heat rapidly exceeds 121 degrees Celsius, pushing the bearing steel past its thermal stability limit. Engine bearings are precision machined into a slight lemon shape to compensate for extreme inertial forces at high RPMs. Superheated without oil, this delicate geometry is completely destroyed. The metal swells inward from thermal expansion, and the clearance hits absolute zero. The friction reaches the fusion threshold in a phenomenon known as galling. Superheated material is violently ripped from one surface and adhered to the other. The bearings melt and fuse to the spinning crankshaft, instantly stopping the rotation and snapping the heavy connecting rods in half. Engine seizure functions as a rapid thermal chain reaction, turning a precision machine into fused scrap metal in under 3 minutes. During the automobile's infancy in the early 20th century, internal clearances were so crude that cars did not feature standardized oil filters. Drivers simply dropped the oil pan to manually flush out dirt and steel shavings. Today, the margin of error is nearly non-existent. Modern Formula One race engines are built with clearances so tight to maximize compression that they operate completely on the edge of physics. At room temperature, an F1 engine is essentially seized solid. The pistons physically cannot move past the cylinder walls. Before the engine can be cranked, engineers must connect external heaters to pump hot water and preheated oil through the block for 20 minutes to thermally expand the metals into operational tolerance. As manufacturing evolved to demand higher RPMs and tighter internal geometries, modern engines simultaneously became vastly less tolerant of neglected maintenance, incorrect fluid viscosities, or any disruption in fluid dynamics. Given the destructive reality of oil starvation, a rational vehicle owner often assumes the solution is simply to add more oil. The logic suggests that significantly overfilling the crankcase guarantees the pump never runs dry. This split-screen comparison shows what happens when an engine is overfilled. The fluid level rises so high that the spinning crankshaft crashes directly into the standing oil. The high-speed rotation acts like a kitchen egg beater whipping cream into foam. This aeration introduces compressible air pockets into a non-compressible hydraulic system. The oil pump cannot build pressure with foam. When these aerated bubbles reach the engine block, they immediately collapse under 70 kilonewtons of combustion load from the rod bearings. Functional oil pressure plummets to near zero. Without the liquid wedge providing physical lift, the metal asperities collide, triggering the exact same extreme friction, galling, and eventual seizure as running the engine completely dry. Overfilling weaponizes the fluid against the engine's hydraulic integrity, removing the safety margin drivers think they are creating. The most dangerous misconception debated on automotive forums is the belief that revving a cold engine warms it up faster. Revving exponentially multiplies the rotational speed and friction, while the fluid is still too highly viscous to penetrate the 0.5 micron gaps. Protecting a modern engine requires strict adherence to precise fluid dynamics. A driver must always utilize the exact viscosity printed on the oil cap, such as 0W20. Modern variable valve timing systems require incredibly thin oils to circulate instantly. Utilizing a thicker oil significantly delays startup flow and accelerates bearing wear by up to 300%. Fill levels must be maintained strictly between the min and max dots on the dipstick, checked on level ground, to prevent both catastrophic oil starvation and fatal foam-inducing crankshaft aeration. Vehicle owners should stringently reject heavily marketed aftermarket thickeners and Teflon treatments. High-quality synthetic oils are perfectly chemically balanced. Disrupting that delicate chemistry with cheap additives clogs microscopic 10-micron passages, causing the exact starvation you are trying to avoid. Finally, extending maintenance intervals allows the oil to suffer from fuel dilution. Testing shows that even a 10% dilution of fuel into lubricating oil drastically compromises film strength, directly heightening the risk of explosive crankcase failures. A $50 jug of correct viscosity synthetic oil is the absolute cheapest insurance policy in the world against an $8,000 catastrophic failure.